Hello everyone, in this video we are just going to implement and use Systick timers in STM32F4466RE microcontroller, which is based out of ARM Cortex M4 processor. Let's get started. So as the first step, let me just explain you what is the thing that I'm going to do in this video. So we are just going to implement periodic interrupts using SysTick timer of ARM Cortex M processor. So for that particular ARM Cortex M processor, we are just going to use the microcontroller STM32F4466RE. And as the next step, since we are going to implement the periodic interrupts, that is, we are just going to implement the SysTick timer interrupt in a regular accurate time delay cycle. So since we are going to implement it in a periodic way, we are just going to blink an LED which is available by default in the Nucleo F446RE development board. So let me just open the user manual of the development board. So this is the user manual of the development board that I'm using, that is Nucleo F446RE. So here you can clearly see there is an onboard LED LD2 which is connected to PA5 of the microcontroller. So I'm just going to blink this particular LED LD2 that is available in the Nucleo F446RE development board and which is connected to PA5 of the microcontroller in a periodic manner using SysTick timer interrupt. So system timer interrupt we are just going to utilize for blinking that LED. So PA5 onboard LED toggling out of SysTick interrupt, and we will be visualizing this particular output waveform from PA5 using DSO. That is, we will be checking whether the output that we receive or the time that is produced from the SysTick interrupt is accurate with the help of oscilloscope. So this we will be doing. So this is the process that we are going to do, and we will be varying and seeing the interrupt cycle. So first we will toggle the onboard LED for every 1 second. That is, we will be generating periodic SysTick interrupts for every 1 second in our program, and later we will change the period of the wave generated. So later we will change the wave to 100 millisecond each. So for every 100 millisecond we will generate the SysTick interrupt and we will be toggling the state of PA5 onboard LED. So first we will be toggling the state of PA5 LED with an accurate time for 1 second for each togglation, and later we will vary the period of togglation to 100 millisecond. So this is what we are just going to do. Let me just create the project in Keel Microvision IDE. So we created the project for our microcontroller STM32F446RE, and I am just going to open one of our previous program that we have already written. So this is one of the LED blink program that we written in very first interface lecture of interfacing LED with our STM32F446RE. So this is the program for blinking the onboard LED that we have already written step by step in the first ever interface lecture of this series. So I hope you watched that lecture. So if you are not sure about the configuration done right over here and the logic written right over here in this program, please go back to that lecture of interfacing LED with STM32F446RE in the same tutorial series. You will find that video. I don't want to waste your time explaining the same configuration that I did right over here. I'm just copying everything written right over here and I'm going to paste it inside the main source file created for this project. So the configuration done is very simple. Here we configured the PA5 pin of the microcontroller. Here we just turned on the internal oscillator for the microcontroller. Here we just turned on the GPIO port A clock for utilizing the GPIO port A to which the PA5 LED is connected. Here we just configured the PA5 pin as output pin, and here we just initialize the type and speed of the same port pin PA5. And in this logical part inside the while of 1, we just turned on the LED and waited here for some rough loop delays, and again here we just turned off the LED and here we just waited here for rough loop delays. So this is just a rough loop delay. I'm just deleting everything right over here. I don't want anything, or I will just comment it out. I don't want anything inside the while of 1, and also I don't want this delay, so I'm just going to comment this also, this particular function definition also. And now coming to the configuration of SysTick Timer. In the previous video we just discussed what is SysTick Timer and what are all the registers required to be configured for SysTick Timer, and also we discussed in detail how it is functioning, right? So I'm just going to open that PPT which we discussed in the previous video of SysTick Timer explained in ARM Cortex-M processor. So this is the formula which we use for calculating load value for the timer, that is for generating timer interrupt, and this one or these are the registers which is useful for configuring the SysTick timer. One is the control and status register, another one is reload value register, and this current value register is useful for monitoring the SysTick step value. So we will not be using this current value, we will be loading the load value to the register, reload register, and we will be enabling the SysTick timer with the help of control and status register. So you can clearly see, as I mentioned, we are just going to set 0, 1, 2 bits of this particular SysTick control and status register for enabling the clock source of the SysTick timer as processor clock, and for enabling the counting down to 0 assert SysTick exception request, and also for enabling the counter. So these 3 bits needs to be enabled in this particular SysTick control and status register. So bit 0, 1 and 2 must be enabled in this SysTick control and status register. So let me just try to find the SysTick pointer. You can see SysTick pointer is with the name of sys capital T I C K, and when I try to point to any of the registers available in this SysTick, you can clearly see there are 4 registers: control, load, value, calibration. So let me just point to control register, and again I'm just going to use the same pointer SysTick control or of 1 left shifted by 0, or of 1 left shifted by 1, or of 1 left shifted by 2. So we successfully configured and started the SysTick timer, and now as per the calculation that we did previously, for generating SysTick interrupt for every 1 second in our program, the load value that needs to be returned to the reload register is 1600000. So this is the load value that you want to write to the reload register for generating timer interrupt or SysTick timer interrupt for every 1 second in our program. So let me just use the same pointer SysTick and now point to load register, and I am going to load the value 1600000 minus 1. So since the value starts from 0, 0 is also considered as value, so we will be subtracting 1 from the actual value that we calculated. That's all about the configuration that you want to do for enabling the SysTick timer. and you don't need to enable the interrupt required for the SysTick since it will be already enabled. You just enable the counter and you are going to utilize the SysTick handler now. So now we just want to find the SysTick interrupt handler function. So move to the startup code, just click on the plus near the device right over here and move to the startup code, and here let me just search for SYS. You can see this is the SysTick handler. Copy this, and below the main function I am just going to implement this definition of the SysTick handler. And inside this SysTick handler I am just going to toggle the state of PA5. So GPOA ODR is equal to GPOA ODR XOR of 1 left shifted by 5. So this particular line will toggle the state of PA5 pin of the microcontroller. If the pin is initially high, it will make it low. If the pin is initially low, it will make it high. That's it about the statement written right over here. So that's all about the program that we are going to write. Let me just explain you the program. After the configuration done right over here, what happens is we calculate the load value for exactly 1 second. So when the timer is enabled right over here, the program execution enters into the while of 1 and it will be staying stagnant since no line is written right over here. It will be held inside this loop because nothing is written right over here. And once the value of SysTick timer reaches 0, so as per our calculation, after 1 second, this particular SysTick timer will reach the value 0. So when it reaches the value 0, the SysTick peripheral in the ARM Cortex M will interrupt the NVIC controller, that is the nested vector interrupt controller, and the nested vector interrupt controller will interrupt the processor, saying that the SysTick interrupt has occurred. So the processor will be pausing whatever it was doing right over here and it will come to the SysTick handler written right over here. And after executing everything written inside the SysTick handler, the processor will be resuming back to the same line from where it left or from where it paused before moving to the SysTick handler, and it will continue execution in the same while of 1 in the logical section of the program. So for every second, that is for every time when the counter value of the SysTick reaches 0, this will happen. That is, this particular SysTick handler will be executed once. So the toggling of LED will be happening. That is, toggling of PA5 will be happening for every 1 second in our program as per the load value calculated. So once the load value becomes 0, again the current value register will be loaded with the reload value register value. Again the same process continues. So for every 1 second this particular toggleation happens. So what we will get here is we will get 1 second on plus 1 second off pulse in PA5, which means total time period is 2 seconds and the frequency of pulse generated is 1 divided by time period, that is 2 is equal to 0.5 hertz or 500 millihertz. So we will receive a pulse of 0.5 hertz or 500 millihertz in the PA5 pin. Let me just check that. I'm just going to dump this program. I'm just compiling this program. Now I'm just going to dump this program. Before dumping, click on the options for target, debug, settings, and make sure that your board is connected properly. You must see the ID code right over here, and in the output tab click on the create hex file right over here. I'm just going to dump the flash. The dumping is successful. I'm just resetting the board. You can clearly see in my oscilloscope, I have already connected the oscilloscope probe to the PFI pin of the microcontroller and ground to the ground of the microcontroller. You can clearly see the pulse of 0.5 Hertz or 500 millihertz is generated, which is having on time of 1 second and off time of 1 second. So this is the output which I got in the hardware. And my onboard LED is now blinking. So now coming to the program again, now I'm just going to reduce the time of interrupt right over here. So now the time period for every interrupt occurrence is 1 second or 1000 millisecond. So what if I'm going to reduce, so if I want to reduce this particular time for every interrupt to 100 millisecond, I just want to adjust the load value right over here. So let me just move to the PPT. So now in this case we calculated the load value for generating SysTick interrupt for every 1 second, so that we substituted 1 as the value right over here, which means 1 second time delay will be happening between each and every interrupt occurrence of SysTick timer. So for generating timer interrupt or SysTick timer interrupt for every 100 millisecond, I just want to substitute 100 millisecond right over here. 100 millisecond is nothing but 100 divided by 1000 millisecond. This is 100 millisecond. So whatever the time delay that you want to generate using SysTick interrupts, you just want to substitute the timer delay value in this place of time delay in this formula for calculating the load value. So I'm just substituting 100 divided by 1000 for the value of 100 milliseconds. So 100 divided by 1000 is nothing but 0.1. So when I evaluate this particular expression, 0.1 divided by 1 divided by 1600000, this 1600000 will come to the top, meaning that 1600000 0.1 into 1600000 will be my load value. So what I will get is 1600000. So this will be my load value. 1 0 will be neglected. So I'm just going to delete this. So here what happens is, for every 100 millisecond, I will be getting the interrupt call right over here and the PFI pin will be toggled. So here I will get 100 millisecond on and 100 millisecond off pulse. So the total time period is 200 milliseconds and the frequency of pulse generated is 1 divided by 200 milliseconds, which is nothing but 1000 divided by 200, that is 5 Hertz. So I will get a 5 Hertz pulse generated with the on time of 100 millisecond and off time of 100 millisecond with 50% duty cycle. So this is what the expected output is. I'm just going to compile this program and I'm going to dump the program to my microcontroller. I'm resetting the board. You can see the pulse generator is having high pulse of 100 millisecond, low pulse to be 100 millisecond, and the total time period is 200 millisecond and the frequency of pulse generator is 5 Hertz. This is the output which I got in the hardware. So I hope you learned the methodology for implementing SysTick interrupt request in ARM Cortex-M processor in this video. The process steps remains the same irrespective of the microcontroller. If the microcontroller is having ARM Cortex-M core, this registers are common for ARM Cortex-M, not particular to any microcontroller. If you are working on any NXP or TIVA series microcontroller which is also based out of ARM Cortex-M, you can use the same registers because this SysTick is doped into ARM Cortex-M and not to any microcontroller specific peripheral. So I hope you learned how to generate accurate time delays with the help of Systick Timer in STM32F4466RE microcontroller. See you in the next video. Thanks for watching.